For decades, the standard model of particle physics has served as our primary predictive rulebook. But while its accuracy is confirmed by experiment, the model relies on empirical constants, numbers that must be measured in a lab and inserted by hand to make the equations balance. This suggests the continuum mathematics we rely on may be a top-level rendering of a deeper, discrete architecture. The standard coordinate systems act as a translated interface for a more primitive computational grid. At the hardware level, the universe operates on a Tetra native substrate. Space consists of primitive lattice sites, where every site possesses exactly 4 active interaction ports. When we fundamentally shift from cubic bookkeeping to Tetra native adjacency, we change the foundational geometry of the system. In this framework, arbitrary constants resolve into predictable network overheads and closure frequencies. The traditional cubic coordinate system uses a 26-neighbor addressing shell, but the native substrate only supports 4 interaction ports. Forcing a 4-port geometry onto a 26-neighbor grid mathematically leaves 22 empty channels, creating exactly 22 ghost directions. This creates a systematic error called the near-miss principle. Anytime a calculation distributes physical data across these non-existent ghost channels, it incurs a translation overhead. This geometric mismatch explains the messy fractional decimal found in fundamental constants, like specific force ratios. Instead of invisible fields, the strong nuclear force maps as the network energy keeping a lattice stable. A stable proton closure consists of 3 components. Each contributes 4 native ports, forming a 12-port loop. Standard physics projects this over 26 cubic directions, yielding 0.115. But the native tetrahedral calculation divides the square root of 2 by 12 native ports, giving 0.11785. This specific calculation accounts for the normalization factor required to dictate the true handoff frequency of the closure. Strong coupling emerges as the structural handoff cadence of a 12-port configuration running on a 4-port grid. This structural accounting redefines mass as persistence burden, the continuous computational cost the network pays to prevent a winding pattern from disintegrating. These matrices show the raw discrepancy in processing demand. A minimal stable spiral, like an electron, requires a domain of only 256 nodes to sustain itself. A proton requires a configuration manifold of 19,683 nodes. The mass hierarchy follows these persistence burdens. A proton is heavier because its intricate winding costs the network more. The fine structure constant provides another test case for this coordinate mismatch model. Laboratories measure this electromagnetic coupling strength with extreme precision, yet its specific value remains an unexplained empirical input. This equation shows the inverse fine structure constant breaking into 2 distinct parts, a dominant integer threshold of 137 and a fractional remainder of roughly 0.036. The 137 represents a discrete handoff ceiling. The 0.036 remainder is the orphan residue, the signature generated when tetrahedral packing is forced into cubic bookkeeping. The fractional tail of the fine structure constant emerges as the ultimate fingerprint of a coordinate mismatch. If the geometry predicts mass and coupling, it must also govern how these particles propagate. A 4-port node lacks inversion symmetry, meaning its geometry cannot be mirrored perfectly across an axis. Because of this asymmetry, an ordered sequence of port traversals does not mathematically equal its mirror-reversed counterpart. Attempting a mirror-reversed traversal forces the network to absorb an inversion debt. Left-handed traversals function as low-cost closures, while right-handed paths exceed the admissibility threshold, manifesting as weak chirality. The no-elevator theorem dictates that every step of movement through space requires traversing ordered ports. Every translation inherently involves a rotational winding update. Parity violation is an unavoidable consequence of routing network traffic through an asymmetric port grammar. When traffic hits a dead end, the boundary reconciliation axiom dictates how the network resolves failed handoffs. Inside a closed lattice, when an update token cannot complete its path, it creates an internal burden. We perceive this failed processing energy as heat, but at the exterior edge of the network, tokens interact with empty void. At this exact external boundary, an unspent update token is instantly converted into a completely new spatial unit. Cosmic expansion proceeds as this hardware-level minting of new space, an outcome of the same handoff failures that manifest as heat. Accepting this model requires us to move past the illusions of cubic overcounts. The smooth curves of continuum space are a conceptual overlay built on a discrete lattice. The Tetra native compression theorem demonstrates that the empirical scaffolding of physics reduces to network geometry. Fields are transport corrections, couplings are closure frequencies, and masses are persistence burdens. In this light, particles are not static objects that move, they are stable transport grammars navigating an underlying grid. The standard model remains a powerful tool, but it is only a rendered user interface. Reality is compiled node by node on the Tetra native substrate.